In our last lecture, we had looked at linear regression. In this lecture, we are going to be looking at linear models for classification. Towards the end of the lecture, we will look at how one can deal with problems where one needs not a linear but a nonlinear model for classification. So let's get started. Let's start with a binary case. So in the case of a two-class problem, what we need to do is we need to define our model as shown here. That is, if the input is from class 1 letters or from positive class, then we want this sum to be greater or equal to 0. On the other hand, if the input is from negative class, then we want this sum to be less than 0. So essentially what we are going to be doing in this model is that we will be finding these parameters wi's and w0, and then we will sum up the values for a given input, and then that summation or score will be compared against a threshold to decide whether the output should be +1 or -1, indicating whether at the input we have an example from positive class or an example from negative class. And of course, in order to find the model parameters, we need a number of examples. So let us assume that we are given n pairs of examples, and these examples come from two classes. Now, if you look at this quantity out here, this basically defines the equation of a line when you are dealing with problems where the number of features is 2. If you are dealing with problems where you have more than 2 features, then this equation describes a decision boundary consisting of a plane or a hyperplane. The parameters of this equation that are involved here do affect how the boundary is going to be placed and how it is going to be oriented. So the location of the boundary is controlled by W0, and W transpose or weight vector W or parameter vector W controls the orientation of the boundary. If you look into the right-hand panel, I've shown you two different lines, or you can say two different decision boundaries or two sets of parameter values. And depending upon what parameter values you have, you can see that we have different orientations for the lines and we have different locations for the line. Another important point to be remembered here is that if you calculate the value of this expression W0 plus W transpose X for any given input X and take an absolute value of this expression, then that absolute value basically indicates how far is observation vector X or observation point X from the decision boundary when you are measuring the farness or the distance in a perpendicular manner. Obviously, we need to define a loss function so that we can figure out the parameter values given a collection of training examples. So to do that, let's start with a function that we call as an indicator function. And I'll show you how this indicator function can be used to figure out what is the number of misclassified examples. So this indicator function is defined as shown. So this function is going to be 1 if the argument of the function is true, and this function has a value 0 if the argument of the function is false. Now let's look at the expression shown here, and let's look at the argument for the indicator function in this particular case. Let us consider the case where yi, that is the desired output, is +1. That is, the input example is supposed to be from positive class, and we expect our model to produce an output that indicates that input example is from the positive class. And of course, for our model to do that, W0 plus W transpose Xi has to be positive. So if yi is positive and W0 plus W transpose Xi is positive, that means no error is being made, then the value on the left-hand side of the inequality is positive. That means this condition is not satisfied, and the indicator function will return a value of 0 in this particular case. On the other hand, if yi was 1 and W0 plus W transpose Xi produced a negative value or a negative score, then obviously the inequality of the indicator function is being satisfied, so it will return a value of 1. And of course, when it returns a value of 1, we know that since W0 plus W transpose Xi was negative, for yi to be positive, that means our model made an error. And you can work out similar numbers for yi to be negative and see whether it produces a 1 whenever there is an error or not. So essentially, this loss function that we have basically is capturing the number of misclassified examples. And if we were to plot this loss function for different possible values of our parameters, then this loss function is not going to be a continuous smooth curve, but it's going to be a curve which goes up and down in steps, which means that this function, when it varies with w, varies not in a continuous smooth fashion, but it is jumping from one point to another. And any function that is showing that behavior obviously is not good for gradient search. So we cannot really use this function for gradient search. However, we can make some modifications to this function to make it suitable for gradient search. So let's see how we can do that. So let's make a modification, and this modification you can see here is made by adding or by multiplying the indicator function with another quantity, which is nothing but just the score produced by our model, which is W0 plus W transpose Xi. So now one thing we have done is that because this score is a continuous number, so our JW in this case is going to exhibit more smooth behavior. The problem here is that W0 plus W transpose Xi could be positive, could be negative, even when the errors are being made. So the issue with this loss function is that terms in the summation on the right-hand side of the expression JW basically will be positive sometimes and negative sometimes. That means there is no clear way of indicating when this function is reaching its minimum value. So what we need to do is to make a small modification, and let's do that in the next slide. So what we do is we basically make another small modification and rewrite our loss function as shown in the top expression. And if you carefully pay attention to this expression, you will find that what this expression is doing is it is defining a loss function where we calculate summation of this over those examples that are being misclassified. And if there is no misclassification, obviously JW will be 0. If there are misclassifications where we have defined this expression, the function JW will always be positive when there are errors being made, and it will be 0 when there is no error being made. So this looks like a good function to be used for gradient search. And in fact, this is what we will do as a first step. So if we take this function and calculate the gradient, then we can define our updating rule or learning rule to find the parameters as shown here. That is, the new value of our parameter vector W is going to be old value plus alpha times summation over all misclassified examples of yi times xi. This rule is known as perceptron learning rule. And we will be coming back to this rule when we start talking about neural networks. And again, we can implement this rule in the batch mode as the expression is written, or we can increment it in the incremental mode. In the incremental mode, the updating will take place whenever there is an error that is being made, whenever there is a misclassification that is being made. If there is no misclassification being made by the model, then no updating will take place in the incremental mode. Now, let us see how we can extend this model for those classification problems where the number of classes is more than 2. That is, multiple classes. So suppose the number of classes is C. In that case, what we will do is we will use C different weight vectors or C different models, one per category or one per class. And what we will do is we will have each model produce its output, or its output is score W0 plus W transpose X. And then we'll say, all right, we have C scores because there are C classes, and we will decide in favor of that class whose score is highest. So this idea is shown here in this picture. So you can say that, all right, on the input side, we have an input vector which is consisting of 4 numbers, 1, 8, 4, 2. And we have 3 models. There is a model for a cat, and the parameters of that model are 0.7, 2, 4.5, and 2.5. There is a model for dog whose parameters are 0.5, minus 2, 4, and 4.5. And there is a model for car, and the parameters there are minus 1.2, 3, 4, and 6.4. So in this case, with the given input, we can calculate what is the score of each and every model. So the cat model produces 39.7, dog model produces 9.5, and car model gives us 51.6. 51.6 being the highest score. So we say, all right, on the input, what we are looking at is a car or a pattern that represents car. So that's how we will deal with multiple classes. Now let's look at another loss function which we call as SVM loss function, or support vector machine loss function. And to understand this loss function, let's look at this problem here in 2 dimensions from 2 classes. So we have bunch of training examples coming from, let us say, blue class, and then we have a bunch of training examples coming from a red class. Now if you were to use a linear model, obviously one can draw a line between these two groups of red and blue dots, such that on one side we got all blue dots and on the other side we got all red dots. And as you can see here, infinite number of lines are possible. Intuitively, if I was to ask you to draw a line or pick a line, chances are that you are going to pick a line which is somewhere in the middle of the gap between these two groups of points. Or to put it in another way, you are going to be picking a line which can be considered as a fat line. And the idea being that such a line will give you enough margin, because what you are looking at is a small number of training examples. But when you put your system in practice, it is likely to encounter some variations from training examples. And to deal with those variations, what you want to put your line somewhere in the middle, or you want to make your line fat, as we are seeing. So basically, what one can do is, or one can look for a solution where you are putting a line somewhere in the middle so that it has sufficient margin on both sides of the decision boundary to deal with future variations in the examples that the system is likely to encounter. So if you move your line, a red line, on both sides up and down, you can see here that as I move upwards, here is an example from one class, and when I move my line on the other side, here is an example from the other class that first hits the line. So these examples that hit your boundary as you move your boundary up and down, these examples are known as support vectors. And a support vector machine basically builds its decision boundary in terms of such support vectors. And the process of finding such support vectors is actually an optimization process, not similar to gradient search, but much more complicated. We are not going to go through that, but we'll just look at what kind of loss function one can have when you want to have a fat line as a decision boundary. So to take care of the margin, one can write a loss function as shown here. So the loss function for an ith example will be given as j sub I, and this loss function is summation as shown in this expression. And in the summation, we are looking at a function max and taking either max of 0 or wj transpose xi minus wyi transpose xi plus the margin value delta. And of course, if we sum up our loss function over all the examples, then basically we have a loss function for our given collection of training examples. Now let's say that we have only two classes. In that case, the loss function that I have defined above basically turns out to be j sub I equal to max 0, 1 minus yi wi transpose xi. So basically this is a loss function where the margin is 1. If I was to have a different margin, then instead of 1, I'll have some other number there. Now, you might be finding a little bit hard how does this loss function work. So to do that, let's take a look at a very simple example, a single example. Let us say that we have 3 classes. So the loss function looks for 3 classes as shown above. And in this case, we have obviously 3 weight vectors. And of course, we'll have 3 scores, as we saw earlier for multiple cases. Each class has its own score and its own weight vector. So let us say that these scores turn out to be, for a given input, 11, -3, and 7. and let us say that the input is from class 1. And let us assume that we want margin to be 5. In that case, let us see what the value of j sub I, or the loss function for this particular scenario will be. So if you plug in the numbers, so for class 2, the score is coming out to be -3. So we will have -3, and it will subtract -11, which is the score from class 1. And of course, we have our margin of 5. Sorry, a margin should be 6 here. I think I made a mistake there. So let's say margin is 6. So basically, that is the first term of our expression for ji. The second term will take into account class 3 and class 1. So the numbers in this case will be 0, 7 minus 11 plus 6. So if you look at j sub I in this case, it turns out to be plus 2. So what it means is that although the score for our correct class is highest, that is, our system did not make any mistake in making the classification decision, the score is not high enough for the given margin. So basically, our loss function will have some value, which is 2 in this particular case, although the decision being made is correct. So with this loss function, if you were to do some plotting for the binary case, you will come up with a shape which is known as the hinge shape, and the function is known as the hinge loss function. This hinge loss function is shown in red out here, and from here it is flat because the margin is being met there. And in this case, of course, this is an example with margin equal to 1. There are 3 other loss functions shown here. The one in blue is what we call as a 0-1 loss function. That is, there is no loss if there is no error being made, and there is a unit loss if an error is being made. And obviously, that is not good for our any optimization because it's not a smooth function. The black one is what is known as the logistic loss function, and the green one is known as the exponential loss function. The logistic loss function is used in the logistic regression classifier, and the green one, the exponential loss function, is used when we use an ensemble of classifiers. Some of those things we are not going to be talking, but some of those things are actually covered in courses on machine learning. Just to give you an idea of what we, this hinge loss function is basically a convex function, but it is not differentiable at every point. And just to make sure that everybody understands what we mean by a convex and a non-convex function, obviously what you want your loss function to be a convex function if possible. In that case, you have only single minima as shown in the leftmost curve. All right. And of course, this function is differentiable at every point. The rightmost curve is what we call as non or not convex function. And in this case, you can see that there are, in the example shown, there are 2 minimas. One you can call as the local minima, and one you can call as the global minima. And in general, a non-convex function might have multiple minimas. The curve in the middle is a convex function, but it is not differentiable at every point. For example, at this point, it is not differentiable. Now, just to remind you the definition of a convex function. So Let's take a look at the leftmost curve, and let's pick any 2 points from this convex function and join them by a line. Then if the function is convex, then every point on that line will lie inside the convex function. Now let's go to the rightmost function, which is a non-convex function, and let's pick up 2 points. Say 1 point from here and another point from here, and join them by a line. So you can see that when we do that, some of the points on that line are outside the function and some of the points are inside the function, which means it's not a convex function. Now let's see how we perform differentiation or do the gradient calculations when you have a convex function, but that function is not differentiable at every point. And that's, of course, for our hinge loss function. So if you look at your hinge loss function, basically you can say that this function is differentiable on every point on this line. This function is differentiable at every point over here. Only at this corner point, the function is not differentiable. So the answer to getting the gradient for hinge loss function lies in what we define as subgradient descent. And the idea of some gradient descent without going into the mathematics is very simple. That is, if you are sitting on the slanted line, then basically you use the expression as shown here for calculating the gradient. And when you are sitting on the flat or horizontal line, obviously the gradient is 0. So essentially the updating of the weight vector is made using either of the two partial derivatives depending upon the value of the product yi wi transpose xi, which will tell you where you are sitting on this hinge loss function. So that's how this is done in practice. Now let's briefly mention what we mean by regularization and why regularization is important. The idea of regularization is to enforce preferences for solution or for model parameters by adding a term to the loss function. And this term is called the regularization term. The whole idea of regularization is that you don't want your model to memorize, in a way, all the training examples. Because a model that memorizes all the training examples and works perfectly on training examples is likely to give you poor performance when it is going to be put in practice. Because in practice, the examples it is going to deal with are not necessarily going to be training examples. Those examples are going to be somewhat different from training examples. So what you want to control how much your model is going to memorize the training examples. And that control is performed or done by adding an additional term which we call as the regularization term. And depending on the value of lambda, you can control the amount of regularization. And the expression for regularization looks like this. In this case, basically what we are saying is that we don't want model parameter values to grow very big, because what we are measuring here is the norm or length of the parameter vector. We don't want all the parameter values to be large so that the length of the parameter vector is very large. So we are controlling that. So in a way, you might specify 10 parameters, but by controlling the length of the parameters, some of the parameters will end up with small values, while the other parameters will be of decent values to make sure that a reasonably good model is produced. there is another way of doing regularization, and that is using the absolute sum of absolute values of parameter values. Either one is used. The first one, where we are using the square, is known as the L2 regularization, and the one with the absolute values is known as the L1 regularization. Now let's look at another model for classification, and this is known as the logistic regression model. So again, let us assume we have n examples, and goal is to build a model. And in this case, let us say the goal is to build a model that produces either 0 or 1 at the output. And in this case, what we do is, instead of comparing the score W transpose X, assuming that W0 has been absorbed in weight vector W and X has been augmented. So instead of calculating, looking at the score, whether it is greater than threshold or not, we pass this score through an exponential function, which is defined as, or we define the output of our model as 1 divided by 1 plus e to the power minus W transpose X. This function, 1 divided by 1 plus e to the power minus x, is known as the sigmoid or sigmoidal function, and it has a shape as shown here. And basically, because of this function, the output of the model will always be lying within 0 to 1. So let's say that that's the model we are going to be using. And how do we now get updating rule, or what kind of loss function we can define for such a model? So let's look at the cost function for logistic regression. The squared error cost function that we used earlier when we talked about regression, that function turns out to be non-convex in this case, and it's not a suitable function then. So instead of that, the function that is used for this particular model is given by the following expression. That is, J of W is given as 1 divided by n, summation I equal to 1 to n, yi, where yi is the desired output for the ith example, log yi hat. Yi hat is the output being produced by the model, plus 1 minus yi times log 1 minus yi hat. If you look at the expression inside the summation, this expression is known as cross entropy expression. Now, some of you might remember the definition of entropy. Entropy, not talking from thermodynamics point of view, but from a probabilistic point of view, entropy is a measure of uncertainty. For example, if you have a system which has, let us say, only 2 states, where the state 1 has a probability of P1, and system being in state 2 has a probability of P2. Of course, P1 plus P2 equals to 1, because those are the only 2 states that are possible. Then the entropy of that system is basically minus P1 log P1 plus, minus log P2 it will be minus P1 log P1 minus P2 log P2. That's the definition of entropy, and you can see that if both P1 and P2 are equal to 0.5, that means both these states are equally possible, then that expression has the highest possible value. On the other hand, if one state, let us say P1 is 1 and P2 is 0, then the entropy is 0 because there is no uncertainty. The system will always be in state 1. And instead of entropy, if you switch P1 and P2 either before the log or after the log, then you end up with what we call as cross entropy definition, and that is what we have in this particular case. So if we use the cross entropy definition, one can actually use that and minimize the cost function. And in this particular case, the minimization, the gradient turns out to be as shown. And finally, the updating rule turns out to be W new equal to W old plus alpha times target output minus actual output times input, which is X sub I. And again, you can do this in the SGD mode or in the batch mode. Both the expressions are shown here. So here is a simple example illustrating logistic regression. So we have basically 6 points or 6 training examples coming from 2 classes. The first three training examples are from class 0, that is we want the output to be 0. And for the last 3 examples, the output is 1. And if we build a very simple model starting with weight vector initial values as minus 0.31 and 0.6, and go through 2 iterations, basically just for illustration purposes, that is what we get. And at the end of 2 corrections, if we were to look at the weight vector and see what it produces as the output, and if we were to draw the decision boundary using the model weights that we found, that's the result we will get as shown in this slide. So you can see that we have figured out, or we have located a linear boundary which basically separates points from 2 classes. Here is another example using 2-dimensional data. So again, we have generated some points in random, and that's the plot of those points, indicating that we have points from 2 classes, and in this particular case, of course, the boundary is not a linear boundary because we cannot really separate out yellow points from the violet points using a line. But in this case, if we were to apply our logistic regression model, we will end up with a linear boundary which will be doing as best as it can be for this particular problem. So let us see where we are, or what kind of result we get. So in this case, we will use the sklearn library, and basically sklearn library has as one of the linear models logistic regression. So we will import that model, and then we will try to fit that model and then predict the probability for each and every example, whether they belong to class 1 or class 2 or class 0 or class 1. And what we can do is we can even make a plot of those probabilities. So basically that is the probability plot for training examples for class 0. And this is the decision boundary that our model after learning is producing, and you can see that this boundary is not giving us 100% accuracy because that's not possible, because it's not a linear problem, but it is giving us a reasonably good boundary so that we are able to perform classification with minimum error between these 2 classes. Now let's look at what we mean by softmax regression. So logistic regression, as we have defined in the previous slides, basically is working for 2 classes problems. So the question is, how do we extend this model to multi-class problem? The extension is known as multinomial regression. So let us say we are given n examples from C classes, and for every example we are supposed to produce either output of 1 or 2 or 3 depending upon the class label. So in this case again, we will use a separate weight vector for each and every class. So we'll basically have C weight vectors, and we can represent them using a D plus 1 times C matrix, where D is the dimensionality and plus 1 is coming because we have to augment the vectors. So basically D plus 1 times C is a matrix that basically is of weight vectors that will be learned using these examples. So what Softmax regression does is that it produces C outputs whose sum equals 1. So in some sense, Softmax is basically doing the normalization of C outputs that we get from C different models that will be trained. So an input is classified using Softmax regression with the following rule as shown here. So if you look at the right hand side of the expression for y hat, that expression is essentially a normalization expression. And because of the normalization, the y hat values for different i's and different k's will always be between 0 to 1. So with this, what one can do is one can define a classification rule where we say that given input x sub I will be assigned to class. So given input x sub I is assigned to class y I hat k, where y I hat k is greater than y I hat j for all j's 1 to c except j not being equal to k. That means we will essentially classify xi to class k if the yi hat value for class k happens to be the highest after normalization. All right. So that's basically what the Softmax regression does. So far what we have done is we have looked at 3 different models for loss functions and correspondingly how to figure out the model parameters. Now let's consider the question of how do we deal with nonlinearity. Obviously, there are a large number of problems of interest that are nonlinear problems. Two simple examples, or you can say two made-up examples are shown here. One is on the left-hand side, we have data from two classes such that from class 1, all the points are scattered inside a circle in the inner circle, and for class 2, all the points are lying in a concentric ring as shown there, and those points are from class 2. And similarly, we have in the right-hand panel another example of data from two classes where the boundary between these two classes is not a linear boundary. So the question is, when we have problems that are nonlinear in nature, how do we deal with them? One simple approach for dealing with nonlinear problems is to do what we call as polynomial mapping. The idea of polynomial mapping is very simple. That is, what we do is we map our input problem into a higher dimensional space. As an example, let's say that our input variables are 1, x1, and x2. 1, of course, being there because of the augmentation. So with these three input variables, we construct a new set of variables or new features, and let those new features be 1, x1, x2, x1 square, x2 square, and then x1, x2. That means what we have done is we have taken our input variables and constructed a second degree polynomial. So we have now features that correspond to an expression for input variables x1 and x2 in a second degree polynomial. So in some sense, what we have done is we have taken our original data, which was in a lower dimensional space, in x1, x2 space, and we have taken that data and transformed it into x1, x2, x1 square, x2 square, x1, x2 space. That means we have gone to higher dimensions. In general, starting from n dimensions, what we are doing is we are going to n times n plus 1 by 2 dimensions. And with this higher dimension, what we can do is we can now work in this higher dimension and use a linear model. And this example shows how that will work. So we have the original data, which is not separable by a line. So what we will do is we will basically define, let us say, additional features. So basically, instead of x1 and x2 as our feature vector or as our input to the linear model, we will input x1, x2, x1 square and x2 square as inputs to our linear model, and then have the linear model learn the classification parameters. So in this case, if you take the examples in 2 dimensions, map them into 4 dimensions, and then present those mapped examples for training, we will end up, let us say, with a weight vector which basically is like this. And if you look at this weight vector will classify all the examples correctly. And this weight vector, if I map it into lower dimensions, basically represents a decision boundary which can be given by x1 square plus x2 square greater or equal to 2, which is actually the equation of a circle as the boundary. So essentially what we have done is we have solved the problem of nonlinear boundary by mapping these features into a higher dimension. So pretty neat way of doing things. However, there are problems with this approach. What happens is that it's very rare that you are working with 2 or 3 features. Typically, you have many features, 8, 10, 20, 30 features. So in those cases, if we were to do mapping to a higher dimensional space, the number of parameters or the number of coefficients in the higher order polynomial is going to grow exponentially. For example, if you have original space as 64 dimensions, and if you just map the original data to a 2-dimensional polynomial or second order polynomial, then the number of terms in your second order polynomial is going to be 4096. And if you take it to a third order polynomial, then the number of terms is going to be 252,144. Obviously, these numbers are impractical for any practical problem of interest. So the idea of polynomial mapping is nice, but it does not work for real practical problems. There is another way of dealing with nonlinear problems, and this is through what we call as kernel function approach. In the kernel function approach, the basic idea is still the same, that is, perform mapping to higher dimensions, just like we did in the polynomial case. But in this case, use functions that have certain properties so that the method is practical and applicable even when the number of input dimensions is much, much large. So to understand this, let us look at this picture here. So let us say we have a vector x and we have a vector y. And let's say that for vector x, we apply some kind of function phi x. For vector y, we apply some kind of function phi y. And then we calculate phi x transpose phi y. Let's say that we have another function called kxy. And to this function, we input x and y. And let's look at the output of this function, which we'll designate as kxy. One can find a function k such that this output is going to be same as this for all values of x and y. So if we can find such a function, then that function is what we call as the kernel function. Let's take an example. Suppose x is 2 and 3 and y is 1 and 2. Let's take the dot product x transpose y. And in this case, for given x and y values, this dot product is 8. And let's take the square of this dot product, and that square is 64. Now let's look at a three-dimensional space where x is given as 4 root 2, 6, and 9, and y is given as 1 square root 2 times 2 and 4. And if you look at the original x and y and this new 3D space where we have mapped x and y, you can express the relationship as a1 square. The second term is the square root of 2a1 times a2, and the third term is a2 square for any point a1, a2 in the original space. So that's how we mapped x and y into the 3D space. Now let's calculate the dot product of mapped x and y in the new space. You will find that if you do the calculation, that dot product turns out to be 64, which is same as the square of the dot product in the original space. One can try this for another pair of x and y, 5 and 2 and 2 and 7. In that case, the original space dot product and the square of dot product are 24 and 576. And with the 3D representation for x and y, we get the same dot product to 576. Okay, so we can actually compute the dot product in the mapped space without explicitly mapping of the original data into the higher space. That is, we don't really need to start with our original space, map them into new space, store them, and then do the training. During the presentation of input examples itself, if we were to use this function k, we will be able to achieve the results that are equivalent to doing the mapping. So these functions are known as kernel functions, and this shortcut to computation is known as kernel trick. So you might say, all right, how do we define a kernel function, or how do we find such functions? So here are some definitions. A function that takes as its input vectors in the original space and returns the dot product of the vectors in the feature space is called a kernel function. And since we are measuring the dot product, basically you can say that a kernel function is a measure of similarity. And of course, it is defined by implicit mapping phi, and from the original space to the vector space. And of course, the mapping has this property that kxy is equal to phi x dot phi y. So any function that satisfies this, and if is positive, definite, and symmetric, then that function is known as the kernel function. Here are some examples of kernel functions. There's another example which shows you how you can map it, basically similar to what I shown you earlier. That is, in this case, in this panel out here, that's our original data, which is not linearly separable in two-dimensional space. If we map them into three-dimensional space through kernel function, we can find a decision boundary and separate them out. Another kernel function which is very popular is known as the Gaussian radial basis function, which is basically shown here. And another one is known as the sigmoid kernel function that is defined here. The benefits of kernel approach: the linear methods we have seen all use dot products in their models. We're always talking about W transpose X, which is dot product, all right? So any model that uses dot products, one can incorporate kernel approach in those models or in those methods and basically build classifiers for nonlinear problems. And of course, there are several different choices for kernel functions, and generally, depending upon what you choose, you end up with a slightly different learning algorithm. So again, whether you should be choosing a radial basis function or choosing something else, typically comes with a little bit of practice or experience. All right. So before we conclude here on our linear models, I'll show you an example of producing or dealing with nonlinear boundaries. And if you were to use, let's say, support vector machine, and in this case, the data is coming from two classes, and it's a nonlinear problem, yellow and violet. So if you use the support vector machine and use linear kernel, that is, do not use any of these kernel functions I mentioned, in that case, you are looking for a linear boundary. That's all you can do. So in this case, the SVM produces this as the linear boundary, which obviously is not going to give you very good classification performance, but that's the best you can possibly get. On the other hand, if you use the kernel function RBF, or radial basis kernel function, that means before doing any dot product calculation, you make use of the radial basis function and then apply SVM. In that case, you end up with a decision boundary which is nonlinear and is able to do the classification very nicely and perfectly for this problem. So again, there's a lot of literature on kernel methods and a lot of people use them and they have been very popular. But in our case, what we are going to do is we are going to be progressing towards deep learning. So what we want to talk about is another way of dealing with nonlinearities, and that is using neural network approach. So in the case of neural networks, we can deal with nonlinear problems by having an architecture of a neural network where you have one or more hidden layers. And this is what we will be discussing next when we talk in the next lecture. So we will stop here